So we will again touch on this idea of scale selection in time and space, another vast topic that obviously I'll just give a brief introduction in a podcast. We looked already at the scales, so this was the horizontal and vertical structure of the dominant interseasonal variability. We were looking at regressed 10 to 90 day filtered GPCP and zonal and meridional wind anomalies at 850 hectopascal. This is the active period and this is the break period. So obviously there is rain during the active period, but has this kind of a large scale structure with this out of phase relation with the deep tropical region. And I also mentioned this kind of a east-west pattern here, Northeast India core monsoon zone, and of course there is the East Asian monsoon related activities here. During the break period you switch things around, so you can see this whole thing has become negative with some differences, and again the relation here and the relation here. You have the cyclonic circulation here, the anticyclone cyclone kind of thing with corresponding local Hadley cell. And the history of trying to understand and model MISO's monsoon interseasonal oscillations is rather long, several decades. Some key questions still remain. We know that the origin of the oscillations happens somewhere in the deep tropics. I had already mentioned that maybe the genesis of convection in the Western Indian Ocean is something that happens all through the year, and during the MJO season they seem to propagate eastward and then things happen here, but that's the MJO. But maybe during the boreal summer season the eastward propagation leads to a detouring here, but there are also arguments made that many of them come from the northwest tropical Pacific Ocean and so on. And earlier models also worried about whether this can be considered looking at the large zonal scale versus the short meridional scales, whether they can be done as let me turn on the light here, whether they can be done as zonally symmetric calculations, analytical or models that can be looked at as a zonal symmetric problem. But of course the zonal propagation means you cannot have a zonally symmetric representation. It's also not clear whether land hydrology is important, the soil moisture, precedent rain and its impact on land-atmosphere interactions and so on. One also should remember that the northward propagation activity is strongest over the ocean here going into the Bay of Bengal, and this northwestward signature that goes as monsoon depressions and low pressure systems obviously have a strong correlation with the northward propagating systems, but they are not a continuum of northward northwestward propagation. Plus we also talked about 30 to 60 day signals that have northeastward signature, 10 to 20 day systems that have the northwestward signatures, and so on and so forth. Okay, keeping all those things in mind, one of the ideas that has kind of taken hold is by Jiang et al. This is from chapter 10 by Bin Wang on theories on interseasonal oscillations. And the main idea of this paper by Jiang et al. From 2004 was that there is a easterly vertical shear set up, as I said before. Simply in terms of thermal wind arguments, you can say warm Tibetan plateau heating and the relatively colder high pressure ocean should give us a vertical shear, and there is a strong vertical shear of course in the monsoon domain. But as I mentioned, if you look at the mean winds, the zonal winds also have a strong meridional gradient, so there is also strong barotropic instability there. So the question is whether it's the baroclinic instability that is tipping over and giving you kinetic energy for northward propagation, or whether it's the horizontal shear and barotropic instability that is giving you the kinetic energy for northward propagation. Again, these are open questions, but I did want to mention that before we go on to looking more specifically at the propagations at 30 to 60 days and 10 to 20 days. Okay. So these general points of the Jiang et al. Idea is that the vertical shear interacts with the dynamics in this way. So if you imagine vertical shear and curl your fingers, you get the horizontal verticity, which is shown here, and that creates a circulation in the vertical plane, which is shown here as the shear, u bar 1 up here and u bar 3 down here, giving you the vertical shear, and that would give you surface frictional convergence and give you vertical motion and tilt the verticity, and then you can relate it to the existing convection center and get appropriate convergence happening ahead of the existing convection center. So you have the tilting of the verticity this way here and tilting of the verticity upwards here. So you have ahead of the convection baroclinic and barotropic modes getting coupled, and that gives you a sequence of events which would drive northward propagation of convection, which is what we would call MISO. I'm doing it in very simple words, but you can look up Jiang's paper for the calculations. There have been criticisms of this model basically because this works away from the equator, not in the equatorial region where F is 0 of course on the equator, but beta is strong, so this model wasn't good at explaining the initiation of the propagating features from the deep tropics and so on. Okay. And it didn't necessarily resolve the details of land versus ocean and so on and so forth. A new idea has been proposed more recently by Lei Zhou and the Chinese colleagues, which included me as well, which argues that it's the horizontal gradient of or meridional gradient of the zonal winds and the barotropic shear, barotropic instability, and the argument there is that there is a coupling between the sea surface temperatures and low-level zonal winds at interseasonal timescales, which is driving the energy for northward propagation, and that air-sea interaction and the coupling is argued to be related to the deep convection in the Western Pacific and its impact on downdraft over the deep tropical Indian Ocean and the interseasonal oscillation and the shallow convection that's happening associated with the ITCZ that we looked at in terms of the marine ITCZ and the northward ITCZ position or movements. So that horizontal wind shear is then through processes argued to drive kinetic energy. It shows they define what is called a central Indian Ocean mode, which is the EOF, coupled EOF of the SSTs and zonal winds, and they show that this mode index that they create out of it has a high correlation with intraseasonal variability over the Bay of Bengal. Again, it's a hypothesis that is supported in many ways by the consistencies with the northward propagation, interseasonal rainfall, and so on, but the question is far from over in terms of exactly what are the processes that are involved in the scale selections and the propagation speeds and the split of the frequencies at 10 to 20 days and 30 to 60 days and so on. Okay. So we will leave that there and go on to look at more specifically the propagations of the two spectral bands, 30 to 60 and 10 to 20, and add a few more points. But again, this is to say that the science keeps moving forward. You get data, you build a hypothesis based on data, then you seek more data to make a theory, then you want to build a theory to confirm that the theory actually works. And till you get data that contradict the hypothesis or the theory, you assume that the theory is right. So we are still building theories, and as we said, there are multiple theories, and we will visit some of those when we go to later chapters. Okay.